Hello, I-24 MOTION users. Nice to meet you. This is Junyi Ji from Vanderbilt University. I'm now working on the data analysis and help with the post-processing for the I-24 MOTION project. Welcome to our session. In this session, I will guide you through the virtual trajectories for I-24 MOTION, data, and tools. So let's get started. In this session, I will guide you through how to generate macroscopic measurements from the raw data, how to smooth and interpolate macroscopic data based on the adaptive smoothing method, and finally, use the macroscopic speed field, we could generate virtual trajectories for further analysis. All the details of this session can be found at our virtual trajectory paper, which I have attached here. Okay, at the end of this session, you will be able to generate this space-time diagram with both speed mean field and virtual trajectories, which are shown in the black lines. Okay, so these sections will be composed of 3 parts. Part 1 is how to generate the macroscopic mean speed field. Let me guide you through the details. The code here is easy to follow. From the predefined script macroscopic data processing, import the function called getSpeedMeanField, and then we can run the code. So when the code is running, I can explain the parameters I set up here. So since all the timestamps in the dataset is under the standard Unix time, we need a function called convert to CST Unix to transform natural local time to Unix timestamp from a trivial time script. So here we basically use these days morning 7:20 to 7:30 to name it as start time and end time. Input files are these JSON files you want to process with. Here we use the inception data version 1.0, which is November 22 for tutorial. dx and dt here are the size of the space-time box, which I will go through the details late in the next page. We hope to quantify the macroscopic measurements. Here, we define it to be 0.02 mile and 4 seconds. We also need to specify the lane number to have a lane-specific analysis. Here, we could use the lane 1, which is the leftmost lane on freeway, which is also called HOV, high occupancy lanes, in I-24, operating from 7 a.m. to 9 a.m. in morning peak hours. Then we could run the code. I will introduce the way to calculate the macroscopic speed here. Generally, it is under the framework of the famous EDIS definitions for macroscopic measurements. Here we pick up a diamond area and measure the total travel time and total travel distance of all the captured trajectories in the area. Then the mean speed is estimated by the total travel distance by total travel time. The diamond area can enhance the homogeneous of the traffic considering the wave propagation pattern. For more details, we recommend the users to read the reference attached here. Okay, here we go. About 40 seconds, we process the 10 minutes data. To visualize the result, the code is also predefined. Import the function called visualize heatmap. Then we could have the space-time heatmap colored by the speed of each observation point. The x-axis is a time and the y-axis is a mile marker. The color bar is also attached on your right. However, as you can see from the plot, though we have put a great effort to improve the upstream processing procedure, There are still missing data and some anomalies here. Then the question comes, how to smooth and interpolate these macroscopic speed data? In part 2, I will navigate you through the answer to the questions. ASM is called adaptive smoothing method. That is a smoother we used in this part. Here, we could import the predefined function called smooth raw data and run the one-line code. When the code is running, I want to show the general high-level idea of this smoother. The main idea is to separating the mean speed field in two entities, free flow speed and the congested field. Following this division, the method can make these two speed fields calculate separately. For the free flow speed field, it will wait more for these directions of the free flow wave speed, which are considered as 70 miles per hour here. And for the congested part, we can consider the congested, that is called the wave propagation speed. And in these directions, it will give more weight to interpolate and smooth the data. So the wave propagation speed here is set up minus 13 miles per hour, which is opposite to the traffic flow directions. For more details about this smoother, users can refer to the paper attached here. Then we have a smooth speed mean field. It can be used for many traffic flow modeling purposes. We can see the smoother keeps the most of the traffic patterns we can observe and nicely interpolate the missing values. In the last part, if we want to quantify the travel time starting from different times through the testbed, we need a virtual trajectories to help with us. Virtual trajectories here are defined as a virtual vehicles follows the mean speed field, basically to solve the ODE I attached here with a speed mean field, which is called VS. Here, we could also import the predefined functions called getVT, K, and K here refers to the number of the virtual trajectories we send to the testbed sections. Since we only show 10 minutes data for tutorial purpose, we send one vehicle to enter the testbed. To overlap the virtual trajectories with the heat map, we could use the functions visualize heat map VT. The plot shows how virtual trajectories go through these congested areas with the procedure of slow down and speed up. For more data, users could follow the steps shown here to generate more virtual trajectories to quantify the difference in travel time. More analysis related to travel time can be found at our paper. That's all. Thanks for listening. Welcome again to the world of I-24 motion data.